All right, so this is the last example on page 5 of your notes. And all that we've done so far is different Friedel-Crafts types of reactions. And what happens in that type of reaction? Well, we have to form some type of super electrophile. So that's what is going to happen here. But one thing you'll notice about this is that we don't have aluminum 3 chloride, we don't have an alkyl halide, so it's not going to be the most standard type of Friedel-Crafts reaction. But what is the Friedel-Crafts reaction doing? It basically forms a super electrophile. And in those cases, the super electrophile tends to be a carbocation. If it's a secondary or tertiary alkyl halide. So somehow the alcohol in this reaction must react with the sulfuric acid to form a carbocation. So maybe take a minute to pause the video and try and work that out. Try and make sure you can figure out how does a carbocation form from these different reactants, and then try and use that carbocation in this Friedel-Crafts to predict the product and draw the mechanism. So pause the video. Boop. Good job. I think you got it. But just to make sure, let's walk through this. So we learned last semester that alcohols with sulfuric acid will essentially protonate, right? It's an acid-base reaction. So that alcohol would protonate. So how does that change things? Well, now instead of having OH, which is a very poor leaving group, OH can't really leave because it's O-, and that wouldn't be very stable. We now have water as our leaving group, which is a much better leaving group. So this can take the electrons from that carbon-oxygen bond to leave, which would then give a carbocation, which is our super electrophile in these Friedel-Crafts types of reactions. So once we have that carbocation, the benzene ring is going to do the same thing that it does during all of the Friedel-Crafts reactions. It's going to add to that carbocation to make a new carbon-carbon bond. And use the wrong alkene, or the wrong pi bond. So we added the cyclohexane ring there. We have our carbocation in that position because this carbon here lost a bond, so that means it's going to be positively charged in that structure. Now we have to reform the aromaticity somehow. How does this happen? Well, we have some type of base that is going to deprotonate this hydrogen, and the electrons in that pi bond are going to come down and reform the alkene, or the pi bond, which will reform the aromaticity. So what bases do we have around? We have the conjugate base of sulfuric acid, but actually a stronger base than that would be the water molecule to the left. So we can draw that water molecule to the left right here. That's going to come and grab that proton. The electrons in that are going to go form the aromaticity in that structure. And now we have our cyclohexane substituted benzene ring. So that's what you would predict from these reaction conditions. Great job with that. I hope that everything is making sense. We are now going to talk in the future about directing effects. So these have mostly been unsubstituted benzene rings. Now what happens if we have a substituent on it? What type of constitutional isomers get formed? So those are the questions we're going to tackle. So having a good understanding of these basics about how what reactions we can do is a good step to being able to understand kind of the regioselectivity, so which constitutional isomer is going to be formed. So we'll get to that. That's pretty fun. That's up next. So I will see you then.